Dear students, welcome back once again. So now I am going to discuss about the most vital topic of the chapter heat and thermodynamics, and that is first law of thermodynamics, the title of which I have already mentioned in the previous video. But if you can remember, that is during beginning of this chapter and during discussion or explaining of the term thermodynamics, I already mentioned that is one of its definition. That is, thermodynamics is such a branch of physics which deals with the interrelationship between heat energy and work done. That is mechanical energy and heat energy. And through so many examples in the previous video, we have already explained that heat and work energy are interconvertible to each other. That is the example of the cooking, isn't it? That is the running of the steam engine by the steam of the water, then rubbing our hands, isn't it? Then burning the coal, and then the electricity. From the electricity energy to the heat energy of the electric heater, we can iron our clothes, isn't it? Then inserting air into the tires of the bicycles. So all these examples we have already seen that to get certain amount of heat energy, we need to do certain amount of work, and whereas to do certain amount of work done, we need some certain amount of heat energy. So work done, that mechanical energy and heat are proportional to each other, and this is the very fundamental and general form or statement of first law of thermodynamics. But this is not only ample, it means a lot. It has some broader and detailed expression. Okay. So let's talk about the first law of thermodynamics. What does it state? The first law of thermodynamics states that whenever some heat is supplied to a body or to a system, then this supplied heat energy works into two forms, into two ways. That is, some part of heat energy is used to increase the internal energy of the body or the system, that is increases temperature, and the rest part is used up by the body to do external work done, to do external work against external agent, that is external pressure, which I have already mentioned through the example of the bulging of the balloon, isn't it? It is work done by gas. So it means if 100% of energy is heat is given to a body or to a system, in some part it may be 40% or 50%, 60% is used up. That is no certain amount. It is some part of is used to increase its internal energy, which I have already learned. It's total kinetic energy and potential energy of the molecules is the total internal energy, which is heat energy. Okay, so that is gone. Then rest part is utilized by the body or the system to which the heat is supplied to do some work, to fighting with the external pressure, to its expansion, isn't it? But here, providing system condition is that the system has to be totally thermally isolated from the surroundings. What do you mean by totally thermally isolated? It means it cannot get influenced by the surroundings. It means there is no exchange of heat. There will be no exchange of heat between the body and the surroundings, isn't it? The no heat will enter from the surroundings to the body, and the no heat can escape from the body to the surroundings. It's called thermally isolated. Just like some it's just like insulated from each other. Thermally isolated, thermally separated, insulated. It means when one system cannot get influenced by the other. It means when other cannot affect, if any system cannot be get affected by the others, or other cannot affect one system, then they are called totally insulated or isolated. A very example, it can be explained through a very easy example. Suppose five friends are listening to some song, a particular song or five different songs, without using headphone, that is on the speaker of the mobile. Then what will be the result? Then all the songs or the five songs, same song or different song, will superimpose, and it will create a cacophony, isn't it? It will be just a disorder, it will create a pandemonium situation. So nobody will listen, nobody could be able to listen to the song, to any song with ease, isn't it? Clearly. But now just imagine if they use the headphone, if they listen to the songs with using the headphones, or then without disturbing anybody, they can enjoy the music without superimposing, without disturbing. This is called thermally isolated. In case of electricity, it is called insulator also. Okay. So it means when any body cannot be get affected by something, one cannot get any influence, any impact on the other. Okay. Free from any disturbance. This is called thermally isolated. So it means there will be no exchange of heat between the body and the surroundings. It's called thermally isolated. Okay. So let's see its mathematical expression. So suppose before heating, the initial internal energy of the body or the system is E1. Clear? Now the applied heat is Q. Q is the total amount of applied heat. Now since the heat is already supplied, so internal energy obviously will increase. Heat energy is increased, internal energy will increase, so this is U2. So that's why U2 is greater than E1. Since before heating internal energy was E1, after applying heat its internal energy will obviously increase because the molecules will get the kinetic energy will increase by getting thermal energy, and some of the kinetic energy will be converted into heat energy, which will obviously lead to the result of increasing its temperature also. So and the external work done by gas equals to W. So according to first law of thermodynamics statement that some part of the supplied heat is used up to increase this internal energy, that is heat energy, which in turn called temperature. Rest part is used to do the external work by the gas against external pressure. So you can see supplied heat Q, that is increase in internal energy before E1 and after increasing U2, so total increment E2 minus E1 plus. So this is the first part of the heat which is used up to increase in its internal energy. Clear? And this is the rest part which is used to do the external work done by the gas. Very clear? So this is the pure general mathematical form of first law of thermodynamics. Now if the amount of supplement of heat is very less, dq, and due to that if the change in the internal energy is very small, so obviously in that case the work done by the gas will be obviously dw. So this for small heat, small increment in internal energy and small work done. So du plus pdv, because we have already seen that is the work done by gas externally is the expression is pdv. So dq is equal to du plus pdv, or q is equal to delta u, or we can express that at delta u. Okay, so q is equal to delta u plus w. So these two are the authentic mathematical expression of first law of thermodynamics. This is, since we have already learned that the heat, and so this equation establishes an interrelationship between mechanical work and the heat. So that's why it is called the alternative form or another form of law of conservation of energy. Since condition is that this system is totally thermally, has to be totally thermally isolated. So obviously whatever energy we are supplying we will get in the other form. This is nothing but law of conservation of energy. So we can say the first law of thermodynamics is another form of law of conservation of energy. Okay. So now one thing. So the implication of the first law of thermodynamics. Now the first law of implication of thermodynamics we have already explained. Okay. In the previous videos also, that is, it establishes a relationship, interrelationship between the mechanical energy, that is work done, and the heat energy. It means by spending some heat energy we can perform some work, or by spending some work or doing some work we can generate some amount of heat energy, isn't it? It means to get certain amount of heat energy we need to do some work, or to perform some work we need some heat energy. So in this sense, so it means it is impossible. So without spending anything, without spending any energy, we cannot perform any work. But without spending any work, without doing any work, we cannot get any heat energy. Or without any heat energy, we cannot perform any work. Okay. So it means it is impossible. It is impossible to without expending anything, without expending nothing, we cannot get either work done or heat energy. We have to do some work. We have to do some energy. We have to expend some, to do some work, we need to supply some energy. Without spending energy, it is impossible to perform work. So the implication of the first law of thermodynamics that it says that it is absolutely impossible to invent such a machine which can work for eternal, okay, for perpetual life, okay, without spending any energy. It is absolutely impossible to invent such a machine which can work perpetually for long and long, eternally, without spending energy. So this is the implication of first law of thermodynamics. It means if we want to do work, we have to spend some energy. Clear? Without spending energy, a machine cannot work. Okay. But before that, we need. Okay, I would like to say something about the internal energy of a gas. We have already discussed about internal energy of a body. That is, it is total kinetic energy and the total potential energy of the molecules. Okay, and total is called internal energy or heat energy of a body. But in case of a gas, the thermal state of a gas depends on three factors, three quantities, that is temperature, pressure and volume. But the fact is that in case of a gas, its internal energy depends only on its temperature, neither on its volume nor on its pressure, because it has been experimentally proved that at a constant temperature, with the change in its either volume or pressure, its internal energy, there is no change takes place in its internal energy. Okay, at constant pressure, if volume is increased or pressure is increased or changed, if volume is changed or pressure is changed, there is no effect in its internal energy. Means its internal energy remains unchanged, unaltered, constant, either in its change in pressure or volume. But with the change in its temperature, there is significant change in the internal energy has been observed. So that's why it is called, in case of gas, its internal energy or heat energy is purely depends on its temperature, neither on its volume nor on its pressure. But it is only applicable in case of ideal gas, because in case of real gases, it has been seen that its change in its internal energy changes very slightly, very small, with the change in its volume. But it is so negligible, so small that it can be avoided, it can be neglected, it can be ignored. So we can say in case of any gases, its internal energy purely depends on its temperature, neither on volume nor its pressure. So now this is the first law of thermodynamics. Okay, but we know there is another law, that is second law of thermodynamics. So what are the limitations, faults of the first law of thermodynamics, so that we need another law? Because of that, we have already learned that heat energy and work, mechanical work, are interconvertible to each other. Okay, but we don't know if some heat energy is converted into mechanical energy or mechanical energy is converted into heat energy, whether 100% of energy is interchanging here or not. It means if some amount of energy is converted into, whether 100% of heat energy is convert into mechanical energy or not, or if from mechanical work we get some heat energy, then whether 100% of mechanical works or mechanical energy converts into heat energy or not, we don't know. There is no mention. First law of thermodynamics, there is no mention, no sight of these lines in first law of thermodynamics. We all know that some amount of heat energy, if we do some work, some heat energy is produced. But whether 100% of heat energy work done is converted into 100% of heat energy or not, it is not mentioned in first law of thermodynamics. Again, if we want to get some heat energy, we need to do some work, isn't it? So 100% of work done is converted into heat energy or not, or whenever heat is applied, isn't it? Through heat energy, to perform certain amount of work, we need some heat energy. In this case, whether we perform some work, that is by using heat energy, that is burning, that is during cooking, that is using the steam engine runs on the work, isn't it? By burning the coal, using the steam, we generate electricity. In that case, whether 100% of heat energy is totally converted into 100% of mechanical energy or not, so there is no mention in the first law of thermodynamics. Again, certain amount of mechanical energy converts how much amount of heat energy, or certain amount of heat energy produces how much amount of mechanical energy, there is no mention, it's totally absent. So this is the limitation of the first law, which leads to the origin of another law, which is called second law of thermodynamics, which we will discuss in the next video. Okay.